Math 2414, Power Series Video 4, third example. Determine for which values of x the following power series converges. In other words, find the domain of f of x. We have a function, capital J0 of x, equal to the sum of from n equals 0 to infinity of -1 to the nth power. So we have an alternator, times x to the 2n over 2 to the 2n times n factorial squared. Just a quick side note, this is called the Bessel function of order 0. It shows up in physics and engineering. Bessel functions are solutions to a particular type of differential equation encountered when studying wave propagation and static potentials. I need to fix the grammar here. It's going to bother me. There we go. Solutions to particular types of differential equations encountered when studying wave propagation and static potentials, neither of which I can tell you anything about because I'm a theoretical mathematician, not an applied mathematician. I can tell you that when you take a course on differential equations or courses on differential equations, it's not uncommon to represent the solution to a differential equation as an infinite power series, which is why they're kind of important to study at this level. All right, so we're going to find the values of x for which this series converges by using the same approach that we used before. We're going to set up the ratio test and require that the limit be less than 1 to guarantee convergence. Now, we also have to explore the possibilities of when the limit is equal to 1, since the ratio test is inconclusive when that limit is equal to 1. All right, so let's set up the ratio test. And remember, when you set up the ratio test, by definition, or rather by the theorem, I should say, the ratio test starts by taking the limit of the absolute value of the ratio of consecutive terms, what I dub the next term compared to the current term being the one that you see. The next one you get by replacing each n with an n plus 1. But when your term is a ratio or a fraction like this one currently is, then you can be a little bit more proactive about setting this up and write it as the next term times the reciprocal of the current term. So we're going to do that. We're going to set this up as the next term times the reciprocal of the current term. Let's go ahead and write the reciprocal of the current term by putting 2 to the 2n on top and n factorial squared on top, -1 to the n on the bottom, and x to the 2n on the bottom. And then for the next term, we will just copy the term that we see, but replace each n with an n plus 1 carefully. I'll show you what I mean. The -1 to the n becomes -1 to the n plus 1, not a problem there. But the x to the 2n does not become x to the 2n plus 1 because the n is being multiplied by 2. So when I replace the n with an n plus 1, I need to put it in parentheses to make sure that the entire n plus 1 is getting multiplied by 2. Same thing down here on 2 to the 2n. That'll become 2 to the 2 times n plus 1. And then the n factorial squared will become n plus 1 factorial squared. And this looks like a big old mess, but it's going to clean up pretty nicely. The first thing I want to point out is that the absolute value completely kills the alternators, because the alternators are either equal to 1 or -1, and the absolute value of both of those is 1. As far as everything else, it might behoove us to distribute the 2's across the n plus 1's when applicable. So for example, the x to the 2 times n plus 1, we can distribute and write that as 2n plus 2. And the same thing down here on the, let me make this a little bit more spaced out, on the 2 to the 2n plus 1. 2 to the 2 times n plus 1. If we distribute that, we can write that as 2n plus 2. All right, so let's see what kind of canceling we can do. Let's start with the x's. On the x's, we have x to the 2n plus 2 on top and x to the 2n on the bottom. We can subtract the exponents, and that will leave x squared on the top. these x's cancel all but these. This is getting a little bit messy, so we're going to start taking inventory of the things that remain. All right, so all the x's cancel except 2 of them on top. Let's see what happens with the 2 to the powers of. We kind of get the same phenomenon here. We have 2 to the 2n right here, and 2 to the 2n plus 2. And if we subtract those exponents, we'll get 2, but this time the 2 will remain on the bottom since there's a greater power on the bottom than on the top. If you do top minus bottom power, the answer goes on the top. If you do bottom minus top power, the answer goes on the bottom. So we're going to get the same canceling effect there. These 2's will cancel those, but leave 2 to the second power, which is just 4, but I'm going to write it as 2 to the second power right now. But what about all these factorials? Well, maybe we need to take those to the side and look at them separately. We have n factorial squared over n plus 1 factorial squared. But since it's just a quotient of squared terms, we can write it as a single fraction squared. And we already know what happens here. It happened in the previous video, or the one before that, no, the 2 videos ago, where when you expand the factorials, on the top you get n times n minus 1 times all the way down to 3, 2, and 1. But on the bottom you get n plus 1 times n minus 1 all the way down to 3, 2, and 1. Don't forget all this is squared. And so everything cancels except the n plus 1 on the bottom. So we're left with 1 on top and n plus 1 on the bottom, but everything is squared. So we get 1 over n plus 1 squared. That means that we have an n plus 1 squared in the bottom of this fraction. All right, so that's really the worst part, just cleaning up pieces, 2 pieces at a time, corresponding pieces with each other, the factorials, the powers of x, the powers of 2, and carefully seeing what's left over. Let's take this to the next page and see what happens next. All right, we got the limit as n approaches infinity. By the way, this is what our L equals, of the absolute value of x squared over 2 squared times n plus 1 squared. Well, the absolute value of the x squared is independent of the n, or rather vice versa. Well, they're independent of each other. I can pull the absolute value of the x squared out because it has nothing to do with the n that we're taking the limit of. And everything else that remains is positive, or even the x squared is non-negative. So technically we could have lost the absolute value a while ago, but let's get rid of it now. We're left with 1 on the top since we pulled the x squared out. On the bottom, 2 squared is 4, and I'm going to leave the n plus 1 squared factored. I'm not going to multiply it out because really all I'm concerned with is this limit. Well, what's that limit equal? Well, what happens to a fraction when this top is static, in this case 1, and the denominator is approaching infinity? Well, that limit approaches 0. So this approaches the absolute value of x squared times 0, but that's just 0. So our limit is actually independent of the x. This limit will always be 0. So since this limit equals 0 for all x's, then the series converges for all x's. Its convergence is independent of the input of the function. So in other words, it converges on the interval negative infinity to infinity. Does not matter what value x equals. Remember, these are values for x's. This is our domain, so to speak. Doesn't matter what x equals. This series will always converge. So it's a little messy, but you know, you're in calculus 2 and the algebra is going to get ugly, and you just have to deal with it at this point. All right, so that example wasn't too bad. It looked messy, but at the end, the limit was 0, meaning it didn't matter what the x was, so the series always converges.